Hello. Yeah. In this video of our series on machine learning using R, I would like to talk about how to perform supervised dimensionality reduction using partial least squares, PLS. So we have seen many unsupervised dimensionality reduction methods such as principal component analysis. But there are cases where the labels of the responses are available, so we can actually do dimensionality reduction related to the response variable. For example, the linear discriminant analysis can lead to a linear discriminant, which kind of summarize all the variables into one score, and that score can be used to do classification. Okay. Partially square is a method that maximizes the correlation between the linear combinations of predictors and the linear combination of the responses. Okay. So it is a very powerful multivariate method, but in this case, we're going to work with just one dependent variable, the response variable y, and we have multiple predictors. So we want to find, we call PLS scores, which are linear combinations of the original variables, but we want to maximize the correlation between these PLS scores and the response variable and see if we can achieve dimensionality reduction. Okay, so let's set a random seed. Now we want 100 sample size, 10 variables. Of course, PLS is really good for very high dimensional data. Okay. So we can create the raw X variables and put in correlation structure. PLS is powerful for handling variables with multicollinearity, so correlated predictors. Okay. Generate the X matrix, and then we assume the Y, the response variable, is related with the the first three variables plus some random noise, and then we combine them into one data set, give them column names, and before we do the dimensionality reduction, we scale the data set. Okay, so now we load the library called PLS, which is the R package for partial least squares. Set a random seed, and we fit a partial least square regression model using the function PLSR. So you can see the syntax is y tier.x scaled, and income equal to 10, validation equal to quote CV, and data equal to data set. So here, income equal to 10 means we want R to compute up to 10 PLS components, which are linear combinations of the original variables. For dimensionality reduction, hopefully only a much smaller number of components are important. For example, they explain the majority of the variance. Okay. And the validation equal to CV means we use internal cross-validation to estimate prediction errors of using 1 to 10 PLS components. So we can use that information to select the optimal number of PLS components. Okay, so let's just feed this model. It takes no time, and then we can print out the summary. You can see the summary here. The most important part is the validation RMSE table. It's the cross-validation using 10 random segments. You can see the intercept, then 1 component, 2 components, 3 components, up to 10 components. Then you have the raw cross-validation, you have the just cross-validation. So the raw cross-validation tend to have some bias due to small sample size. So we can apply an adjustment, a correction, to get the adjust cross-validation value. Okay. So from here you can see from intercept to one component, two components, three components, four components. When we have four components, the adjusted CV reached the lowest value, 0.9007. And after four, you get five components. It went up a little bit, and then went up a little bit. So you can see the smallest one, the smallest adjust cross-validation error was achieved with four components. Okay, this will guide us for selecting how many components here. But this cross-validation error is just one dimension we look at. We also look at this training percent of variance explained. You can see one component, two components, up to 10 components. So you can see to explain the variance of y, for one component you explain 84.35%. With two components, you got a 95.21%. Three components got a 97.27%. Four components got a 97.8%. So basically, when you reach like four components, they're just not like very big increase in variance explained. So even with like four component from like 3 to 4, that's not big jump. And if we can tolerate a little bit difference, there's not much gain from going from 2 components to 3 components. So actually we can make a decision, even though 4 components leads to the smallest adjusted cross-validation error, from the variance explained point of view, we can select 2 PLS scores. Okay. So for here, let's do some model evaluation. So we have fitted this partially square regression model. We can extract certain data from that model to evaluate the model fit. For example, we can use the function called the validation plot. So this putting in the PLS model, you can say the validation type is RMSEP. Okay, so this will show this graph. So you can see it's the number of components, then you get the RMSEP. So you can see the error drop from 1 to 2 a lot. Okay, and then it drop a little bit at 3, drop a little bit at 4. But compared to the drop from 1 to 2, the drop from 2 to 4 is actually pretty small. Okay. You can print out, this is what we have seen in the summary table, but we can use these line of command to say which one lead to the smallest adjusted cross-validation error. So here this tells us 4. Okay, but even that is the case, we can still use 2, but so let's just use 4 here. We can compute the scores. Okay, so we're going to extract, reduce the dimensions. That's a fancy name for the PLS scores. So just use scores, PLS model, and we say n component equal to 4. We can print out the first 2 scores. You can see PLS1, PLS2. The PLS1 explained 84.84%, and then PLS2 as 95.2%. This all agree with the previous summary table. We can evaluate predictions using the predict function to calculate the predicted response values, and then we can compare with the residuals. And then you can see we have the observed y versus the predicted y. They're pretty much agree with mostly along the straight line. So the prediction is pretty good. We can also, again, go back to the summary table, and we can just print out the variance explained was 84.4% for the first component, and then it's like 95% for the two components. We can also print out the loadings to look at the importance of the variables when they are loaded onto component 1 and component 2. So for component 1, it looks like all 10 variables are loaded about equally, like equal weights. Okay, but for component 2, you have some, like x1, you have 0.442, but then for x5, you got 0.024. So there are some differences in the importance of the variable when they're loaded on the components. Okay, so component 1, component 2, or component 3, component 4, these are kind of reduced. PLS scores you can use to replace the original raw data. This is, remember, in the context of predicting the response Y. All right. Okay. Thanks for watching.